So really, the goal of this video is to cover just a few things that are small, kind of minor topics that are in the standards. They're not outdated, but they're kind of on the side, and they're not covered within the chapter 7 and 8 OpenStax that directly. And they're just in like a couple of multiple choice questions, like 1 out of 30 or something like that. So there's a chance you could see it on the exam. So that's why it's called Chapter 7/8 Miscellaneous. So the first thing is bond order and its implication for resonance. For resonance. Now, bond order is just the number of chemical bonds between a pair of atoms. And that sounds like it might be complicated. It's really not. So an elaboration, if we have a triple bond, like in N triple bonded to itself, that is a bond order of 3. In acetylene, here between the carbons, a carbon-carbon bond is also a bond order of 3, but the CH is a single bond, so the bond order is 1. Okay? And then, as that suggests, a single bond, bond order 1. Double bond, bond order 2. Triple bond, bond order 3, right? And remember that a triple bond has the most energy and the most attraction, right? And because it has the most energy and most attraction, then the nuclei can get the closest together. Because remember, what limits how close the nuclei get together in a covalent bond is the repulsion, right? And at some point, the repulsion would overcome the attraction. But if the attraction was greater, then the nuclei get closer together. So as the bond order goes up, there's more energy in the bond, and it's also a shorter bond, right? Which is not new information. We've already covered that. The only thing is knowing bond order, single bond 1, double bond 2, triple bond 3, okay? The only kind of, it's not gimmick, because this is chemistry, it's not really gimmicks in chemistry, but the only gimmick for the AP Chem exam, I guess, is how this would apply to resonance. So remember in chapter 8, we talked about resonance, where a double bond could go in multiple different places. And we also talked about, I like how your book defines resonance as people who had never seen a rhino before, and one person says it's like a hippo, and the other person says it's like an elephant. But it's not that a rhino is this creature that transforms between an elephant and a hippo. It's that it's somewhere in between, right? And so in resonance, if we have multiple bonds that could be single, could be double, it's not really that they're single or double at any time. In this understanding of resonance is that they have some single bond character and some double bond character. They're in between, and therefore the bond order itself is in between to indicate that. So we can still calculate bond order in a resonance structure. Depending on how intuitive this is for you, the following formula might not be necessary, but you could add the sum of the bond orders, or find the sum of the bond orders, and then divide by the number of resonance structures. But I think I'm imagining it should be intuitive for you, but in case it's not, you can use that formula. So like here, in ozone, in O3, this is a double bond, this is a single bond. But if you notice, this would be an example of resonance. So it's not that either bond is actually a bond order of 1. It's not that either bond is actually a bond order of 2. They're both in between, so it's 1.5. Now, again, using that formula, you could do 1 plus 2, right, is 3 divided by 2 resonance structures gives you 1.5. But that might be intuitive for you to just see, okay, it's not a single bond, it's not a double, so split in between, the bond order is 1.5. And that's for you to understand that resonance, like a rhino is not a creature that transforms between a hippo and an elephant. A rhino has some characteristics of an elephant, some characteristics of a hippo, okay? So bond order of 1.5 indicates that resonance is between a double and a single bond. So if you were asked, for example, the bond length, well, the bond length of 1.5 means it's shorter than a single bond, but longer than a double bond. If you asked about bond energy of 1.5 means it has less energy than a double bond, so it's less negative potential energy than a double bond, but more negative potential energy than a single bond. Okay, what about this one? Well, in this example, we can see that there's a double bond, which would be bond order of 2, and then 2 single bonds, bond order of 1. But now we have 3 resonance structures, so it's like at any time, the bond order is like 1 1/3 or 1.33, right? And again, if you're using that formula, you do 1 plus 1 plus 2 for the bond orders divided by 3 resonance structures, and you'd get the same value. So the bond order here is 1 1/3 or 1.3. Okay, so bond order, resonance, and bond length. Remember, single bonds are longer than double bonds, and double bonds are longer than triple bonds. So a bond order of 1.5 would be shorter. Someone knock? Nobody's here. Okay. So a bond order of 1.5 would be shorter than a single bond, but longer than a double bond. It's between the two. Okay, so these topics are not directly related. Again, they're just random things that are kind of like a sentence in the standard somewhere that are not really a focus. So the next one is isomers. Now, isomers are a huge topic. Okay, um, if you were taking organic chemistry, you would learn all about constitutional isomers and geometric isomers, and then chirality and all these different things. And in AP Bio, we talk about it a little bit at the beginning of the year, but it's still, not a focus. There's a lot in chemistry you can talk about with isomers, but I think effectively all they want you to know, and some sparingly given multiple choice problems, haven't seen any FRQs that address this, but I suppose they could, is this understanding of like constitutional isomers in a very, very basic kind of way. So isomers are molecules with identical formulas, the same number of atoms of each element, but distinct arrangements of atoms in space. So they have the same formula, but different arrangements of the atoms in space. So we have the example here, and this question is asking which of the following is an isomer. Okay, so it's the same number of each type of atom or each type of element per molecule, but the way they're connected is different. Well, here we can see it would be C5, and then how many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is C5H12. So effectively, we're just asked, which of the following is also C5H12? Okay, that's all. Again, this is a very basic simplification. That can't be a word. Simplifying of how isomers are, and they're not even gonna like, you know, if you're learning about isomers, this could probably be flipped and it just shows the same image but in a different layout, and you say it's the same. I haven't seen anything like that for AP Chem, so I don't think they're assessing you on that. I think they just want you to understand that there's constitutional isomers, and that they have different bonds but the same formula. So if you look at these, for example, yeah, this is option A is C5, but then there's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. H10, that's not an isomer because it's a different formula. But if you were to count down here, it is C5H12, so this is an isomer. By the way, this question is from Khan Academy. Okay, so there you go. And for what I mean by like changing the arrangement of space if you looked up this exact question on Khan Academy, C and D are incorrect, but the reasons why they're incorrect has to do with like the way they drew it, and even that kind of thing. I haven't seen any AP Chem questions in any question I've ever seen that talks about that. So if you see one, let me know, but I haven't seen it. Okay, so here's the second type of practice problem that you could have with isomers. Which of the following is an isomer or isomeric with CH3, CH2, CH2OH? Okay, so then we can just say, okay, what's the formula? Carbons 1, 2, 3. Okay, so C3, hydrogens 3, 5, 7, 8, C3H8, and then 1 oxygen. Okay, so which of these matches that? Well, in the first one, not enough carbons. Second one, there's no oxygens. Third one, yeah, we have 3 carbons. We have how many hydrogens? 3, 5, 8, okay. And 1 oxygen, that looks good. So I think that's the correct answer. Let's just check the last one though, okay? So in the last one, we have 1, 2, 3 carbons, so C3, and then H is 3, 4, 5, 8, and then oxygen 1. So what am I missing here? Why is it D? Let's count that one more time. Why is D not also a correct answer? We have carbons 1, 2, 3, then hydrogens 3, 4, 5, 8, yeah, and 1 oxygen. I think that formula is weird, but I should have checked this question better. But yeah, these are both correct. So essentially, as long as it's the same formula, it's an isomer. Okay? That's all they are asking for. So we can say C or D here. Which shapes, last thing, again, you can see these aren't that strongly related. Which shapes are considered planar? Which shapes are considered planar? So what does it mean? Planar means that the atoms bonded to the central atom are all in the same plane. So like, this is something hopefully you've talked about in math class, right? Like I have my periodic table here, right? If I got it perfectly flat, it's like one plane through space, right? Like it has an x-axis. It's hard to hold perfectly flat. It has an x-axis, it has a y-axis, but no z, right? So it's all in one plane, okay? So it doesn't go into the z-axis. And so you can see like a plane depicted here. Hopefully you're familiar with this idea from math class. So which of these bonds are flat? Because you could be asked, is it planar? Or you could be asked, is this bond in the same plane as this other bond? So, electron geometries of linear. So if it's electron if the electron geometry or electron region is 2, then it's linear. Yeah, that's planar. Okay, it's all in the same plane. If it's trigonal planar, either if it's electron geometry of trigonal planar, either molecular geometry of trigonal planar or molecular geometry of bent, either way, it's all still in one plane. Okay? So that is also planar. Tetrahedral, no. None of those are all in one plane. Like you can see, right, there's several sticking down and then the one sticking up. There's no way you could put a piece of paper on that, right, and capture all the atoms in one plane. So nothing in with 4 electron regions, electron geometry of tetrahedral, none of those. Okay, then electron geometry of trigonal bipyramidal. In terms of the molecular geometry, the ones that are planar are T-shaped, because the 3 molecules, right, you have the 2 linear ones, and then one sticking out to the side like that. So they are planar in the sense that I can get my piece of paper and have it lined up with them. Now we can look at the molecular models, and maybe I should have when I was showing this, but you can write the 2 atoms up and down, and then one in the axial position, you can all get them in one plane, like with a piece of paper. And then linear again here as well. Then if we're looking at electron geometries of octahedral, well, in terms of molecular geometries, which ones are planar? The pyramid and octahedral, no. But again, we have square planar. So now they're all, as it implies, in a plane. All the atoms that are not the lone pairs are in a plane relative to each other. And then we have T-shape again and linear. So those are the ones that are planar. Now, you could memorize this, or you could also just have this visualized in your head. And hopefully we'll get a little bit of time in class to look at some of the ball and stick structures to help you visualize. But if you can just visualize this, you don't have to necessarily memorize what I just circled here. So the kind of questions you could be asked. You could be asked, which of the following is not planar? Which of these is not planar? And so that would require drawing these all out, right, to determine their geometries here. So BF3 has 24 valence electrons, and I'm going to draw those 3 connections. So that's 6 electrons right there. And then I'm going to include all those lovely lone pairs, 6 per fluorine. So that's minus 18, so 0 left over to put on boron. So that tells me that the electron geometry is trigonal planar, and the molecular geometry is trigonal planar. Okay, so that's planar. Then we go to the next one. We have SO3 that has 24 electrons, minus 6 from my single bonds, and then I'll put the lone pairs on those outer electrons, or outer atoms. So that's minus 18. So now I have 0 remaining. Notice this would be an example of resonance structure because the S does not have 8 electrons yet, so one of those lone pairs can be removed, but it could be from any oxygen. So this is resonance, but that doesn't really apply to the question because we can see that the electron geometry is going to be with those 3 groups, trigonal planar, and the molecular geometry is also trigonal planar, so this is in fact planar. Okay, I'm going to shrink these a little bit, give myself a little more room. Okay, so let's look at these two. So xenon XeF2, I actually don't know how you say it. Xenon fluoride? No, maybe? I don't know. Anyways, it doesn't really matter how you pronounce it. So we have 22 electrons there, 2 times 7 plus 8. And so I can write my basic structure with the xenon and the fluorines there. So that's minus 4 electrons from the 2 single bonds. And then I'm going to put in my lone pairs, 6 on each fluorine. So that's minus 12. That means 6 left over. So that's 3 lone pairs going on the xenon here. Okay, so then we have 1, 2, 3, 4, 5 regions. So this is an electron geometry of trigonal bipyramidal. And then the molecular geometry is going to be linear. So you might say, oh, trigonal bipyramidal, that's not planar. Well, that's the electron geometry, folks, right? So then we have to look at the molecular geometry. The molecular geometry is still linear. So we haven't found our suspect yet. Unless we made a mistake, our suspect is still out there. So let's look at the last possible candidate. So we have SF2, that's going to be 20 electrons. And we have 2 single bonds, so that's minus 4. And now I can put my lone pairs around those. So that's 12 right there, 6 from each fluorine. And so now we have 4, so that means 2 lone pairs on the sulfur. So we have 4 groups, so the electron geometry is now tetrahedral. And that means the molecular geometry with 2 lone pairs is going to be bent. Tetrahedral molecular geometry bent is not planar, so the answer is SF2 here for this one. Okay, so let's look at, oops, don't want to skip to the answer. That would ruin the suspense. So now, planar example question 2. Which of the following statements is true about the geometry of the molecule H2C double bond C, H, OH. So we can draw this out. And I don't know, drawing something like this might be a little bit, I think they would, for something like this, for an AP Chem multiple choice question, I think they'd probably give this structure to you based on what I've seen, my sense of things. So then we need to identify what each of these are. So this first one, I'm just going to write the molecular geometries, is trigonal planar, right? Because we have three groups, no lone pairs. The other carbon is also trigonal planar. And then this oxygen, tetrahedral electron geometry, molecular geometry, bent. Okay, so let's look at what they're asking us about the shape of the molecule. The carbon atoms are in the same plane. Well, if we're looking at this carbon, it's trigonal planar. So that means that, yeah, it's in the same plane because they're bonded to each other in a trigonal planar bond, which is in the same plane. It only has one plane, so that looks correct. Let's look at the other options though. The oxygen atom lies out of the plane of the carbon atoms. No, because as we said, yes, the oxygen is bent, but this is a trigonal. Wait a minute, did I update this question to what I wanted it to be? Let's make sure that. Yeah, I think it's fine. Okay. But we can see that this is still a trigonal planar bond between the carbon and the oxygen there. So because it's a trigonal planar bond, then it's still going to be in the same plane. But like the hydrogen is not going to be in the same plane as the carbon. But the carbon, relative to the carbon, that oxygen is in the same plane because it's a trigonal planar bond. Even though then if we look at the oxygen's bent. Okay, that might make more sense if we were to draw the structure, but basically the carbon and the oxygen will all fit on this plane, but then that hydrogen is going to be bent. So it might be below the plane or above the plane, something like that. So it's not B. The OH bond is linear. No, it's bent. And then the carbon bonded to OH is tetrahedral and not planar. No, that's trigonal planar. So that's not true. So the only correct answer here is A for this one. Okay? So those are the examples of determining if something is planar. I think if you're confused about the carbon and oxygen being in the same plane, again, remember, carbon to oxygen, that carbon is trigonal planar. So the things it's bonded to are still surrounding it in the same plane. But then the things that are bent coming off the oxygen are no longer in the same plane as that carbon. And I think if we look at the molecular structures with the model sets, remind me to if we don't, and I think you can see that pretty clearly.